in fact, we're going to start with working out the example problem I gave you at the end of last class. So what we have is kind of like an experiment where we're given some unknown piece of metal. It could be a ring, it could be a necklace, whatever, and you want to know, what is this piece of metal made of? What type of metal is it? Is it gold? Is it bronze, copper? What kind of metal is this? And you decide, just because you happen to have knowledge of thermodynamics, that the way you're going to do it is by trying to figure out its specific heat. If you know the specific heat of this piece of metal you have, then you could look up in a table of various different metals and say which metal is closest, which specific heat is closest to the one you have. And then you could match up what material this thing must be made of. And the way you do it goes like this. Say you have, well, first of all, we'll have our piece of metal. Here it is. And you're going to stick it in a pot of water, which is really hot. Let's say it's boiling. And the reason you do that is because you want to heat up this piece of metal to a known temperature. And so since water boils at 100 degrees and it can't go hotter than 100 degrees, if you put this piece of metal into the boiling water and you wait a little bit, eventually the piece of metal will get to 100 degrees, just like the water. So now you have your piece of metal at an initial temperature of 100 degrees. Then over here, you have a calorimeter, which is just a fancy way of saying a cup into which, and the cup is made of aluminum, into this cup, you put a certain amount of room temperature water, so kind of cool. And then what you're going to do is you're going to place this hot piece of metal into the calorimeter with the cool water in it, mix it around, put a lid to make sure no heat can escape. And now that's what a calorimeter is. It's basically the vessel in which you could do this kind of an experiment. It insulates itself from the outside world so you don't lose energy to the environment and energy can't come in. Whatever's in the vessel, that's all there is to it. And so now you mix it around, you close it up, and what's going to happen? Of course, the water, the cup, and the piece of metal will all come to the same temperature, some final temperature. And likely what will happen is the hot piece of metal will cool down in the water. And in doing so, that'll heat the water and the cup up to some final temperature. And when you do this experiment and you measure the final temperature, you measure it to be 40 degrees. And so now you take all of this data and you do your calculation to try to figure out what the specific heat of the metal is. And so that's what we're going to do now. Now we're actually going to do the calculation. So the first step in any calorimetry problem is you say, okay, what are all the pieces of my system which are important? And by important, what I mean is those things which will either give off or take in heat. So of course, what we have is the amount of heat due to the unknown metal. And then we have the amount of heat due to the aluminum cup that the calorimeter is made of. And then the amount of heat due to the cool water that you placed the metal, the hot metal into. Okay, so those are the three pieces in my system. And I set it equal to 0. Just like before, as always, Q for each little piece of your system, add all the Q's up, set it equal to 0. Then replace the Q with the equation, which is Cm delta T. So now I'm going to have a Cm delta T for my unknown metal. And I'm going to have a Cm delta T for my aluminum cup. And I'll have a Cm delta T for the cold water. Okay. From this point, it's just a matter of plugging in numbers and solving for whatever the unknown is. Of course, the unknown in this problem is C, the specific heat of my unknown. That's going to be the thing I want to solve. Everything else I should have. So what do we have? For the unknown metal, we need the mass of the metal. And so in the problem, we're told the metal is 250 grams. So we have 0.25. Remember, everything has to be in kilograms, so convert it to kilograms. Then we have delta T, which is final minus initial temperature. Well, I know the final temperature of everything will be 40, and the metal started at 100. Remember, I placed it in the boiling water to heat it up initially. And all of that is multiplied by C, which is the specific heat of the metal. So there's Cm delta T for the metal. I move on. I now have the aluminum. Well, I need a specific heat of the aluminum. That's 300, given in the problem right there. The mass of the cup, well, what's the mass of the cup? You take an aluminum cup of mass 100 grams, so 0.1 kilograms. And then final minus initial temperature of the cup. Well, the final of everything is 40. And the initial of the cup, well, we're going to do like we always do. What we had was an aluminum cup that we put some cold water into. And then we started boiling that metal cylinder over there before we put it in. So initially, the cup, before you put that hot metal cylinder in, must have been at the same temperature as the water was initially. And we're told the water started at 20, so the cup started at 20. So initial temperature of the cup, 20. And then the last piece is the water plus specific heat of water. We're told to use 4,000. The mass of the water, how much water did we have? We placed 500 grams of water. So that's 0.5 kilograms. And then final minus initial temperature for the water, everything got to 40. The water started at 20. And so there we go. There we have all the numbers plugged into my equation. And the one unknown sitting there, the C, is the thing I want to solve for. So at this point, the physics is over with, and it's just a matter of doing the algebra. So what I'll do is I'll go ahead and I will multiply all these numbers out. So the first term, I've got 0.25 times 40 minus 100. Well, 40 minus 100 is the same as negative 60. Right? So 0.25 times negative 60. And that is negative 15. Oops, I don't want to use that color. Blue is my solutions cover. Negative 15 times C. Plus the next term, what do we have? 40 minus 20. Well, that's just 20. So we have 300 times 0.1 times 20 is 600. And then the last term, 40 minus 20, of course, is also 20. So we have 4,000 times 0.5 times 20 equals 40,000. Everything equal to 0. Okay. So I've got numbers, I've got my variable. Let me put the variable on one side and all the numbers on the other side. So I'll move the negative 15C to the right so it'll become positive. So I have 40600 on the left equals 15 times C on the right. Solve for C, just divide over the 15. So C then is going to be 40,600 divided by 15, which gives me 2706.67. And if you want the units, it's going to be joules per kilogram Kelvin. And there we go. There's the specific heat of whatever this unknown material is. If this is an actual experiment in a lab, I would then look up in my table, okay, what material has a specific heat closest to 2700? It may be, 2850, it might be 2775. It's not going to be perfectly this number because this is theory. And in reality, when you do your experiment, you take the metal out of the boiling water, and as you're putting it into the cold water, the calorimeter, it lost some heat before you were able to do so. There's going to be slight mistakes when doing an actual experiment. So the true number may not be the same as the theoretical number, but it's going to be fairly close. And so you would say, well, about 2700. Let me look up in my table. What material is this?
What's the variables on the answer? That's joules per kilogram, you say?
Yeah, it's joules per, and then on the bottom, it's kilograms times Kelvin. And by the way, this is just a trick for, anytime you're worried about units. I don't really worry about units too much in this class, at least showing the units at the end. I know a lot of people love to show units the whole time because, of course, if you keep track of the units, well, if the units are correct at the end, then you must have done the math correctly. But just in case you ever do want to make sure your units are correct, look at the equation. So our original equation, Q equals Cm delta T. What are the units of this stuff? Well, Q, that's joules. Let's leave C alone for now. I don't know what that is. M is kilograms. Change in temperature, well, that's Kelvin minus Kelvin. That's a Kelvin. And so let's solve for what the units of C are. Well, divide over the kilograms, divide over the Kelvin, and I get C has units of joules divided by kilograms times Kelvin. Okay, so just as a little trick, when working with units, if there's ever a variable or something and you don't know what units it should have, look at its equation, solve the equation for that variable, and then change everything to the units instead of the variables. So Q, that's heat energy, it has units of joules. M has units of mass, which is kilograms, and so forth. If you solve for the units in the equation, then you'll get the units of the thing as well. Okay. But yeah, it's joules per kilogram Kelvin, if you want them. So any questions on this particular example from last time?
I have a question. I'm having a hard time. What are we supposed to, how do we know what we're supposed to look for in the problem? Like, it seems like it's different things.
Yeah.
Like, how do I know what am I supposed to plug in for when I'm solving it?
Yeah, excellent question. That's the most important question for sure. What you do, you read the question, and usually towards the end is where it says it, but somewhere in a question, it'll ask you something. So in this case, it says, what is the specific heat of the metal cylinder? So the thing you're looking for is specific heat. And I know the variable for specific heat is C. And of course, there's 3 different items here. So which specific heat? The specific heat for the unknown metal. In previous examples, like over here, it said blah, 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 blah. What will be the final equilibrium temperature? Well, there that tells me the thing I'm looking for is final temperature. So I'd plug all my numbers in, and the thing, first of all, the question says what the thing it is you're looking for. But even if you disregard it, if you go and plug all the numbers from your problem, inevitably there's going to be something that doesn't have a number. So usually that's the thing you're solving for as well. So even if I didn't realize in this example I wanted specific heat, simply by having the equation written out and then replacing every variable I have with whatever data is in my problem, well, I would have had all these numbers, and C would have been sitting there like, oh my God, I don't have a number for C. Well, that's okay. That's the thing you're looking for. Okay, so 2 different ways of going about it. Of course, the best way is the problem's going to tell you. It's going to ask for something, It'll either ask, how much milk should I add? That's what's the mass of the milk. What's the specific heat of this thing? You're looking for C. What must have been the initial temperature of the ice in order for this and this and this to happen? I'm looking for initial temperature. Okay, so the question should give you a fairly strong clue as to what exactly, which one of these variables I'm looking for. And even then, like I said, if you disregard it, by plugging all the numbers you have from the problem, something will not have a number. And that thing must be the thing you're looking for. Okay, so does that make sense?
Yeah, it makes sense. I was talking about, like, you see the green, like
Yeah.
the M aluminum and MH2O in the like, what those, how do you find those in?
Oh, yeah. Okay, good. Yeah, this stuff I wrote here, and I don't know what happened. I guess I just started saying ... for the rest of it. But what was written here was kind of a hint I was given as to go about doing problems like this, because some of these problems have, a whole bunch of different things in them, and each thing has CM delta T. So there's loads and loads of numbers all over the place. And so what I've seen a lot of students do is, instead of just reading the problem, after they wrote down the equation, they read the problem to try to get the numbers out of it, they'll first just list the information. And so what I showed here was, I said, look, if you start reading the question, it says you start with an unknown metal cylinder of mass 250 grams. So I said, look, start making a list. Right here, the mass of the unknown metal cylinder, I'm told, is 0.25. And so it's just sitting there ready to use. And then I keep going. It says you heat the metal up to 100 degrees. Okay, so the initial temperature of that unknown is 100 degrees. And so I write that down. You take an aluminum cup of mass 100 grams. So the mass of aluminum is told to be 0.1. And place 500 grams of water. So the mass of water is 0.5. And just list all the numbers all down, so that when you go and you do this step here, and you want to know what are all the numbers for each one of these things, you can just look at your list. You don't have to read through the paragraph anymore. So I simply took the numbers from the paragraph and made a list out of them. Now these over here, that's just extra information I gave after the problem. I said, look, you're going to need specific heat of water, and I don't tell you in the problem, so I give it to you on the side. But the little box on the left there, it was just a way of listing out the data from the text of the problem, so that you don't have to go back and try to reread the paragraph later on. You just look at the list of data you have sitting there, and it makes it a little more organized. Okay, does that help?
Yeah. My final question is, on the homework, how it says you place 6 bottles of water.
Yeah.
Does that play into the problem at all? Like the 6 bottles, or since it's not asking about that, it doesn't really need to be addressed as far as when working out the problem?
Yeah, it should. For instance, if you imagine, just take, and a lot of times when you have a question like this that pops up in your mind, look at the extremes. So say, okay, the homework problem says something like, I have some bottles of water that are room temperature, and I'm going to put something really cold in with it. And then everything's going to cool down and get to some final temperature. Well, if you have one bottle of water and you put this thing to cool it down, or you have 1,000 bottles of water and you put that one thing to cool it down, obviously that thing that cools it down hits the one bottle of water by itself a lot harder than if I had 1,000 bottles of water, because that's a crap load of water. So it should make a difference. The more bottles of water you have, the more water you have. So what you want to do when you have something like that is, as you're doing CM delta T for the water, and you say, but So this is each bottle of water is this, but I have 6 bottles of water. So just multiply this whole thing by 6. Okay. If you had 12 bottles of water, you'd multiply it by 12. Because what this parentheses thing for the bottle of water is specific heat for 1 bottle of water, the mass of 1 bottle of water, and how does that bottle of water change temperature? But I don't just have 1 of them, I actually have 6. So you're supposed to add this thing 6 times, of course, but instead of adding it 6 times, you just multiply it by 6 because all 6 bottles of water are the same. Okay, so yes, it's very important. And it's a good thing to look out for in a problem. If I say I add a 24 pack of beer to the cooler and I give you the mass of 1 can of beer, well, you don't just have 1 can, you have 24 cans. So you'd have to multiply the beer thing by 24. All right.
Thank you.
Good, good. Any other questions before we move on? All right, so we've pretty much seen examples of the different ways I can ask questions on this form of calorimetry. You're given a system, some set of items you put into the system, each item's at a different temperature. You let it sit for a while, everything comes up to the same final temperature, and then you answer whatever the question is asking. You're looking for specific heat or mass or whatever. What we want to do now is add in the final part of calorimetry, and that is some items that you can place in your system can soak up energy or give off energy even though they don't change temperature. And as an example, let me go to a new page here. Yeah, I think this is all one page. Yeah. So, okay, new page. Lecture 9 starts here. All right. As an example of this process, imagine you have ice. You have a cube of ice. Here it is. Okay. Let's say the ice starts at an initial temperature of -5 degrees Celsius. Okay. And you're going to heat it up. So you heat this ice up. And eventually what happens is the ice heats up until it reaches 0 degrees. Okay. Then if you keep adding heat, what happens is the ice doesn't get hotter. Ice can't get hotter than 0 degrees under normal circumstances. Ice can get all the way up to 0 and then it can't go any further. But you keep adding heat to the system. You keep it on the fire or you put it in the hot coffee or whatever. So instead what happens is this ice melts and becomes liquid water, but that liquid water is still at 0 degrees. Okay, so all you did was melt the piece of ice to turn it into a liquid, but you didn't change its temperature. Of course, you could then keep heating the now liquid water, and that liquid water can go up in temperature. But the ice, as it's ice, can only go up to 0 and no further. So this step right here is extremely important because our equation so far says if I add heat, I must be changing the temperature. Because that's how I keep track of how much heat. If I change temperature, it must be because I added heat. Well, if I don't change temperature, that would imply from this equation, I didn't add any heat. But I know in reality, I did. I kept the fire on this piece of ice and it melted. Well, the whole time it's melting, it's gaining heat from that fire. And this equation doesn't tell me how much it gains. So if I go try to do a calculation, well, there's a crap load of heat I added to the system that I'm not keeping track of. And so obviously all the numbers are going to come out wrong. My prediction will fail. So I have to have some way of keeping track of how much energy I'm giving something while it's doing this process of melting or freezing or whatever the case is. Okay, and what this process or this amount of heat is called latent heat. So specific heat, that tells you, that's the little C here, that tells you how much energy is required to change it by 1 degree, change the temperature by 1 degree. Latent heat is different. This is how much heat do you add to change the phase, to make something melt or something boil or something like that. And this equation is quite easy. Q, the amount of heat you gain or you give to it, is how much of the object do you have, the mass, times a new variable called L. And L is, of course, latent heat.
You said that latent heat is the amount of heat you add to change the phase.
That's right. That's right. So if you have a piece of ice and ice is already at 0, it's still ice. It's not water yet. It's still a piece of ice just sitting there. Now what you want to do is try to melt the ice. And so you're going to change it from solid to liquid. But you're not going to change its temperature. The liquid, when it becomes liquid, will still be at 0. So my first equation doesn't work here. There's no delta T. However, my second equation is, well, if I have this piece of ice, how much heat do I have to add to the ice to make it melt? That's exactly what this new equation does. The L, just like specific heat, it depends on the material. The L depends on the material. Different materials take different amount of heat to freeze or to boil or to melt or whatever the case you're doing is. So now we have this second equation we're going to have to worry about for those problems where it's possible for one of your things in your system to change phase. If you don't have something in your problem that changes phase, then Cm delta T is perfectly fine and you don't need to add anything else. But once you start adding ice to the equation or things like ice, then we better start worrying about this, because if you remember, I said the specific heat, C, of water is 4186. So about 4,200 joules of energy to take a kilogram of water and change its temperature by a degree. Okay, so that's a good amount of energy. Well, latent heat for water, if you have 1 kilogram of ice and you want to turn it into water without changing temperature at all, it actually takes 334,000 joules of energy. Huge amount of energy needed to take this amount of ice or that amount of water and change its phase, to melt it. You're not changing its temperature at all. All you're doing is melting it. So this term, this latent heat thing we're about to add to our equations, is extremely important because that's a lot of energy we have to keep track of. Before we were talking about 4,000, or the big numbers in our examples were things like 40,000 and things like that. Well, this one term by itself is 300,000. So this makes a huge difference if we have a problem where we put ice in a hot liquid and the ice is going to melt. But you see, the equation itself, the little term, is easy. It's just m times L. Very nice.
Will you always give us the L?
Yeah, just like
Will
with
the L always be given?
right. Just like with specific heat. That's not something you have to memorize. I don't believe in forcing people to memorize constants. Unless it's something you have to solve for, unless I specifically say, hey, solve for L in this problem, then no, it's given in the problem. The latent heat of fusion for water is 334,000. Latent heat of vaporization is 125,000, whatever it is. Yeah, you don't have to memorize it. It'll be given in the problem. So let's try an example. There's not much to the theory because we've already done calorimetry. Now all we're doing is adding this extra term. So here we go. example. You start with our classic example with 1 kilogram of hot coffee at 90 degrees Celsius. You place the coffee in a styrofoam cup. And when I say styrofoam cup, all it means is you don't have to worry about the cup in this problem. If I put it in a metal cup, the metal can change temperature. Styrofoam, it's an insulator, it won't change temperature. So that just means don't worry about the cup here. You wish for the coffee to be at 70 degrees Celsius. How much ice should you add if the initial temperature of the ice is -5 degrees Celsius? Okay. Very similar to our previous example where we add cold milk to try to cool off. Here, let's say you don't like milk in your coffee, but you still want to cool off the coffee. So you're going to add some ice cubes. What do we need? We need some extra piece of information as usual. Let the specific heat of coffee be 4,000. Let the specific heat of ice be 2,000. Let the latent heat for the ice, and you could either call it latent heat for the ice or latent heat for the water because it's the same thing. It's going from ice to water. So it's both, is 334,000. And I think that's everything you need to know. So there's our question. We have some hot coffee. We want to cool it down to a new temperature. We're going to place some ice cubes in there until we know the final temperature after the ice melts and everything comes to equilibrium. It'll be at 70 degrees. All right. So how do we go about solving this? Well, now we're going to see why I keep saying the most important part of answering this type of problem is realizing what are all the important pieces of my system. So let's think about it. What's going to happen here? Well, first of all, we're going to have the coffee cool down. So there must be some cue for the coffee. The styrofoam cup, we can ignore. Styrofoam doesn't come into play here. The ice, you're going to start with ice at -5. And once you place it in the coffee, it's going to warm up the ice. So there's going to be some cue to heat up the ice. Then the ice, once it heats up, it can only heat up to 0. Once it gets to 0, nothing's going to happen except it's going to try to melt. So now this ice can melt. So there must be some cue to melt the ice. Okay. Then, now that you've melted the ice, that ice is now called water. It's not ice anymore, it's water. This water, which is at 0, also has to heat up. Because remember, you put the cold ice cube into hot coffee, it melts. Well, that melted water doesn't stay at 0. It's going to heat up to 70 like everything else. So you're going to have to heat up the now melted ice. So I call it melted. Okay, these names I'm putting here, they're my own names. If you have better names for them, if you want to call it Q1, Q2, Q3, Q4, that's fine. To me, C is coffee, ice is the ice while it's still ice. Melt means how much energy to melt the ice. Melted is now that the ice is melted, that thing, that water, can now heat up. I don't call it water. I don't want to say Q water, only because I know there could be other problems where I started with hot water and I add ice to it. And I don't want there to be two different terms that say water, because then I can confuse myself. Was this the initial hot water, or is this the water due to the melted ice? So I just learned to call the water that comes from melted ice, I call it melted. And it just helps me remember this is not the same as the initial water we started with in the problem. Okay? But that's my thing. If you have a different way you want to organize things, feel free to name it whatever you want. But there we go. That's everything in my system. The coffee can cool down. The ice can heat up to 0. Then it can melt. And now the melted ice can heat up to 70. Okay, that's everything in my equation. Set it equal to 0. Any questions about that? That's the most critical part, to know that all 4 of these terms must be here.
I have a question.
Sure.
I don't know if we were done yet, but for these type of problems, that's just the equation itself. We don't do like the CM delta T, because
Oh, we're still
going.
yeah, we're
Oh, okay.
still going to, right. This is just
Okay. I was just,
yeah. No. Of course, it'd be nice if on your test this is all you had to do was write 4 Q's on the page. No, this is just setting it up. We're about to solve it for sure.
all right. Okay. Thank you.
Sure. All right, so now we have our Q's listed. Now let's replace the Q's with what they are. So coffee, what's going to happen to the coffee? Coffee is going to cool down from 90 to 70. So that's CM delta T. So CM delta T for coffee. Ice, what will happen to the ice? Well, this term is the amount of energy to make the ice go from -5 up to 0. Well, that's CM delta T, right? It's just changing temperature, no melting yet. So CM delta T for the ice. Third term, the melt. This is where the melting is going to occur with no change in temperature. So that must be the M times L term. That's the term with latent heat. So they'll call that melt. And then the last term, melted, that is, you've now melted the ice, it's now water. That water has to heat up to 70. Well, that's CM delta T, you're changing temperature. So CM delta T melted. Okay. So there we go. We had, what are all the things in my system, all the Q's. Once I have those listed, I replace them all with either CM delta T or M times L, depending on what that particular term requires. Any term where you're changing temperature, CM delta T. Any term where you're changing phase, M times L. Okay, so any questions about that step? All right, from here, you just plug my numbers in. That's all there is to it. So what do we have? Coffee. Specific heat of coffee, I'm told to use 4,000. How much coffee did I start with? You start with 1 kilogram of coffee, so that's 1. Final minus initial temperature of the coffee. Everything's going to get to 70. Initially, I started with coffee at 90. So there's my coffee term done. I now move to the ice. Here, a mistake can be made, so we have to be careful. Specific heat of ice, well, that's 2,000. How much ice did I start with? That's what I want to know. How much ice should you add? The mass of the ice is the thing I'm looking for, so M, just leave it as M. Final minus initial temperature of the ice. Now, every time we've done an example, I've said everything has the same final temperature. Here, this breaks the rule because ice can only get to 0. That's as hot as ice can ever get. It can't get up to 70. Once it's melted, the water can get to 70, but the ice, that step, can only get up to 0. So for the ice, his final temperature is 0. And his initial temperature, I'm told the ice started at -5. -5. Okay, that is key. I see all the time on homeworks and tests. For the ice term, people will use 70 degrees, the same final temperature as everything. But you have to use some intuition here. Ice, the hottest ice we'll ever get is 0 degrees. So his final temperature must be 0. He can't get hotter than that. That last term we're going to get to, that takes care of the ice, which melts, gets to 70. But the ice never got to 70, the melted ice did. That's something different. Third term, the term where the ice melts. Okay, well, how much ice did we have? We don't know. We call it M. L, what's the latent heat for the ice? That's given 334,000. And now we're on the last term, the now melted ice. So here, again, we have to be careful. The melted ice is not ice anymore. Once the ice has melted, it's now water. Okay, so the melted term, ice is melted, it's water, so we use a specific heat of water, 4186. I didn't write it down with the list, I should have, but again, on a test, it would be given, you don't have to memorize it. How much of this now melted ice do I have? Well, again, it's however much ice I had. I don't know how much I had, I called it M, so it's M. And again, this is another place where mistakes can be made. If what I started with was not hot coffee, but hot water, I see sometimes people confuse this mass of water, because melted ice is called water, this mass as the initial mass of the water rather than the initial mass of the ice. Yes, a specific heat is a specific heat of water because the ice has melted and turned to water. But that thing we're looking at, this one term, is all about the melted ice. So the mass of the melted ice is whatever the mass of the ice was. So it's M. And in delta T, well, the melted water, the melted ice, his final temperature, he'll get up to 70. There's nothing stopping water from getting to 70. So 70, like everything else. And what did he start at? His initial temperature. Well, remember, you started with ice, you heated it up to 0, you melted it. So the melted ice is still at 0. It hasn't heated up yet. So the initial temperature of the melted ice is 0. And there we go. There's my 4 terms. The coffee, the ice to heat up to 0, melting the ice, and then now that the ice is melted, that water will heat up to the final temperature. Set it equal to 0, and we could solve this problem. Because everything's a bunch of numbers, except the one unknown we have in our problem is this mass of the ice business. Now it appears 3 times, so the algebra is going to look a little bit messy. We have to be careful about the numbers here. But it's still just one unknown, one variable, M. So I'm going to calculate everything through, get a bunch of numbers, a bunch of terms with M, collect the M's together, set it equal to the number, and get M by itself. All right, so let me do it really quick because class is just about over. Before I do, though, more important than getting the answer here, do you have any questions about the numbers I plugged in? Hopefully it's making sense. All right, let's do the numbers. So the first term, we have 4,000 times 1 times 70 minus 90. Well, 70 minus 90 is -20. So I have 4,000 times 20 is -80,000. All right, second term, what do we have? 2,000 times M times 0. Well, that's just 0. Then we have 2,000 times M times minus -5, well, that's just +5. So 2,000 times m times 5, well, that's 10,000 times m. All right, third term, well, that's easy. That's just sitting there, 334,000 times m. Last term, we've got 4186 times m times 70. 4186 times 70 gives me 293,020 times m. And then 4186 times m times 0, that's just 0. All equal to 0. So those are all the terms. The first term,
I got a question. Where did the first 0 come from?
yeah. So the -80,000 came from this. Then we have this term here is 2,000 times m times 0. Then this term is 2,000 times m times -5. Okay.
So you did the distribute.
I distributed. Now, of course, if I were smarter, I could look at 0 minus -5 is just 5. I don't have to make it 2 terms. But because there are times where it's 2 different terms and you distribute, I was showing it like it's 2 terms. But of course, if you look at this, you say, look, 0 minus -5 is just 5. So that's just 1 term sitting there. It's not 2 different terms. But in actuality, it's 2. It's just one of them 0. The other one is the term. But yeah, it came from the 2 terms. I distributed through that parentheses. First term is 0. Second term is whatever it is. And then same thing here. 4186 times m times 70, that's this. And then 4186 times m times 0, that's that. Same way, distributed it through. Does that make more sense?
Yes.
Perfect. All right, so quickly, let me get these numbers. I'll collect all the m terms together first. So we got 334,000 plus 293,020 plus 10,000. 637,020 all times m. And then the numbers by themselves, I've got -80,000, and that's it. Well, that's easy, -80,000. That looks a lot cleaner. Get m by itself, I bring the 80,000 over. So 637,020 m equals 80,000. Then divide by the 637 business. 80,000 divided by that thing. And I'm told m is 0.126 kilograms. So how much ice should I put into my hot coffee? 0.126 or 126 grams of ice. It's actually not that much. Notice we have a whole kilogram. That's 1,000 grams of water, of hot coffee. And I only put in 100 grams of ice, and it's able to change the temperature all the way down to 70. So why does it change it that much? Because of this latent heat due to melting. That melting sucks up so much energy from the hot coffee that even a little bit of ice can really change the temperature of a hot liquid. And that's why this is so important. If you don't have that term and you do the same calculation, oh my Lord, you're going to get a completely different answer. So this business of latent heat is very important in calorimetry. If you have a problem where things can melt or boil or things. All right, so there's that example.
What's the
Obviously,
final answer again? Can you
sure,
say the
sure.
final answer again?
0.126 kilograms. There we go. 126 grams if you want. Question?
Yeah. How did you get 0 for the last one, the 70 minus 0 for the melted. I think it was the melted.
Yeah.
Why did you put 0 instead of the 90 for the temperature of it?
Yeah. So remember this last term, I call it melted. And what it means is you had the ice, you warmed it up to 0, you melted it, but in melting it, you didn't change its temperature, right? It stays at 0. And so now it's melted ice, which is starting at 0, and that you put it in hot coffee. So it's going to heat up to the final temperature of 70. So for the melted ice, his initial temperature is 0 because you took ice, heated it up to 0, melted it. And so now there it is starting there at 0, trying to get to the final temperature of 70. The 90 was the coffee. The coffee is separate. He's sitting over there at 90. You put the ice in, but the 90 only dealt with coffee. This last term was all about the ice. What happened to the ice after it melted? And it's always the case that if you have ice and you've melted it, the melted ice always starts at 0 because that's the melting point.
But the 70 is for the coffee too, right?
Right. Remember, the final temperature of everything will all be the same, right? So once the ice is melted and become this liquid ice, he has to heat up to the same final temperature as the coffee cooled down to. Just like the previous examples we did in the past. We put that hot metal cylinder into cold water, swished it around, everything was the same final temperature. Or you put the cold milk into hot coffee, mixed it around. When you take a sip, you don't feel, oh, there's some hot coffee and there's some cold milk. No, everything combines and is all at the same final temperature. So the final temperatures are the same. The initial temperatures will be different, except the one caveat is the ice term, which is the one circled in red there. Notice his final temperature is 0, not 70. And it's 0 because ice can only get up to 0. Once he gets to 0, he stops. So that little term for the ice can't get up to the final 70. So you stop him at 0, then you melt him. Now that he's melted, now he can get up to 70. Okay, so does that make more sense?
Yeah, thank you so much.
Sure, sure. All right, so obviously it's nearly 2. I will let you go in case you have a class or something. Of course, if you have questions, you're free to ask. Next class, we'll do another example, of course, with latent heat. Make sure we're understanding how it works, because on the one hand, it's the same thing we've been doing. But on the other hand, there's small little quirks about it where you have to change a little something, like the final temperature business or the initial temperature business. It's slightly awkward. So we'll do a few more examples, make sure we have it down. But this is all there is to it, to calorimetry. You're either going to have terms because of a change in temperature, or you're going to have terms because of a change of phase. You add all the terms together, plug all the numbers in, you'll be sitting there with an unknown, and you do the algebra to get your unknown. Okay, so this is as far as calorimetry will go for us. But again, we're going to do more examples. All right, so that's all I have. If you have no questions, you're free to go. Don't forget about the homework posted on Canvas. I believe it's due Wednesday, and it's on the first part. It doesn't have latent heat on it. So you could start working on that, of course. And then I will post a second homework, which will have a latent heat problem on it, just so we have a practice for both. But anyway, that's all I have for today. I will see you on Wednesday.
Have a good day.
Thank you. You too.
Have a good day. Bye-bye.
Appreciate it. Thank you.
Dr. Rossman, I'm gonna be out of town in like 2 weeks, so I'm gonna miss the class on Friday the 19th. I was trying to see if like by next week you would know what topics you're covering so I can just watch the video on Canvas.
Yeah. Firstly, I already have all the lectures from last year
Mhm.
pre-recorded, so they will be posted regardless. As we approach, of course, I'll see how far we've gone along with this stuff. I think we'll still be in thermodynamics, so we will not yet have the test, but maybe the test will be close. I'm not going to have our first test till we've done all the thermodynamics topics. But of course, we won't be on calorimetry. We'll be on something else in thermodynamics. But yeah, as we get closer, just remind me and I'll let you know. But even if you don't know ahead of time, you'll see it posted on Canvas, and I'll send an email when the new topic's posted. So you'll be able to see it.
Thank you.
Dr. Rosman, is it possible if you could post the recording for this lecture today?
Yeah, I've been getting them taken off of the cloud for Zoom and kind of editing them a little bit. And I will be posting both like these lecture notes in its own little module and the Zoom lectures we've been doing. I'll be posting them. I just don't know if I'm going to post the straight video or put it on YouTube first and then link it, because there's a certain amount of space it takes up on Canvas. But yeah, these things will be posted for sure.
Okay, it was just, I was just trying to sit back and digest everything. I just wanted to go over it one more time because some stuff was confusing, but okay.
Yeah, for sure. It'll be posted, definitely.
All right.
All righty then.